We're going on to Chapter 4, and Chapter 4 is looking over various means of solving systems of linear equations in two variables. I shortened that up a little bit. And in this first part, we're going to review things from perhaps previous algebra courses. And they introduce on page 170 this word problem. Suppose two adult tickets and one child ticket cost $8. And one adult ticket and three children's tickets cost $9. What is the price of each ticket? Well, you recall that in doing word problems, you need to read it over, kind of get an idea, and then decide on what variables you're going to use to represent things. That's the whole purpose of algebra. So they're suggesting let X equal the price of the adult ticket and let Y equal the price of the child's ticket. Now we can set up an equation. And our basic equation here will be two adult tickets, which would be 2x, plus one child's, and we could put a 1 there, but we don't usually write it. That's going to equal $8. So that's pretty straightforward. And then in the other equation, we're going to say that one adult ticket plus three child's ticket cost $9. So now we have two equations. And notice there are two variables. There's an x and a y and an x and a y. Now we're assuming that the price of the adult ticket is the same in both, and the child's ticket is the same in both, and that it equals this amount of money. So how can we possibly solve that? Well, the first way the book suggests is to make a graph and put these linear equations into the graph, and we're going to see where the lines connect. So I'll get back and I'll have this part done. That keeps the tape a little shorter. So we're going to use a couple of techniques that we've mentioned in earlier lessons, that if an equation as it is in standard form and we want to graph it, a good technique is to use the x and y intercept t-chart. So for this first one, if x is 0, this is 0, then y equals 8. Now in the next one, if y is 0, we're going to divide both sides by 2, and we get x equals 4. Then we have this one. If x is 0, y is going to be 3. And if y is 0, x is 9. So I have two sets. So what I did is I color-coded them. So this is the red equation, 0, 8. My y-intercept is 0, 8. My x-intercept, 4, 0. 4, 0. Then I made the line. Now this equation, it was 0, 3. So we're calling this the blue equation, 0, 3, and then 9, 0. And again, you need to use graph paper for this because the graphing of it is critical. So you're looking at the points of intersection. And this point of intersection is at 3, 2. Now remember, the 3 is the x and the 2 is the y. And if we put it into these equations, 2 times 3 is 6, plus 2 is 8. Checks. And for this one, 3 plus 3 times 2 is 6. 3 plus 6 is 9. It checks. So this is a unique solution for this particular problem where the lines of our graphs intersect. Now, if you used a graphing calculator and put this information in, it would show that they intersect at that particular point. But graphing is a challenge because sometimes if you don't have proper graph paper, you're trying to figure it out. Mine worked out pretty good here. And again, I was careful in doing it. You may not get it. Suppose there are fractions in the answer and they don't go through a really spot on the grid. Then there are other methods, and we'll be showing you these other methods as we go on. Okay, as we move on, and by the way, that previous example was example 1. This is now example 2 on page 171, and we strongly recommend that you look over the textbook and in a sense study it. But what we're trying to do is give you some insight and hearing it explained to you, and that might be helpful. We're asked in example 2 to solve these particular equations, series of equations, by graphing. Now all of them are in standard form. And again, my strong suggestion is when they are in standard form, solve them by making this special t-chart, which will give you the x and y intercepts. So again, if you'd like to pause now, copy this down, and again, what you're trying to do is build up some experience in doing these. By pausing it now, that's what I'm going to do. I'm going to work these out to save, again, a little time. Our results for example 2 are rather interesting. So I filled in the chart, and we've already practiced, hopefully, how to fill it in. To get your y-intercept, remember, is 0, b. That's where your line will go through the y-axis. And this is going to be a, 0, where your line will go through the x-axis. So this is the y-intercept. This is the x-intercept, and I color-coded them for you as well. This one is blue. Okay, so as we look at it, 0, -1, 0, -1, and then 2, 0, and I made my line. Now again, if you use a ruler for this, it really helps. This one is going to be 0, 5, 0, 5, 0, 5. And you see they intersect at this point right here. And that's a very typical type of thing where you're trying to see what set of coordinates satisfies both equations and make the statement true. Now in letter B, again, as you look at them, they look like different equations. They are different equations. And when we plot the x and y intercepts, we get 0, -2, which is right there, and then -4 is 0, and we draw that line. And then here we have 0, 2, which is right there, and then 4, 0. And again, I didn't draw the lines very well, but these lines are in fact what we call parallel. They're never going to intersect. So for a series of equations that are like this, there's not going to be a solution. So we say there's no solution when the lines are parallel like this. There's no point of intersection. And then as you look at example C, you see the equations look different. But when you plot their x and y intercepts, you see they're exactly the same. So when I drew these graphs, one graph is physically on top of the other graph. So what do you say is the solution for this? Well, this is usually written in set builder notation. It looks something like this. We say x comma y is such that, and you write just one of the equations down. Because the solution for one equation is, in fact, a solution for the other equations. They're the same equations in just a different form. So for this, there's an infinite number of ordered pairs that are a solution for each one. And once again, for this one, there is no solution. And for this one, there is one unique solution. Often this is what you'll find. They'll give you these to check your skill for mastery. Now, example 3 asks you to use your graphing calculator, but again, we don't use a graphing calculator as part of this. But at home you can practice if you'd like. The instructions are in the textbook. But we're going on to our next method of solving linear equations in two variables. These are systems where you're assuming the x value is the same in both equations, the y is the same. So here we have two equations. We're going to call this equation 1, and we'll call this equation 2, and they're in standard form. Now, we notice this particular equation has a y in it all by itself. So when we use the technique of substitution, that's what we're looking for. A letter all by itself. It could be the y or it could be the x. Now, what we do then is solve for y. And we do so by taking the 5x, bringing it over, transposing it, it changes its sign. It now becomes a negative 5x plus 4. Now remember, this one now is in slope-intercept form. Just as a little review. Now we know our slope is a negative 5 and our y-intercept is 4. But we've solved it for y. So we say y equals this. So this is a value for what y is. Now we then take our other equation, which we said was equation 2, and where there is a y in the other equation, we're going to introduce this value for y. So we write the 2x exactly the same, the negative 3 exactly the same, but now where the y is, we're going to introduce this value. We are substituting this value for y for the y. But notice, in this value, it's an x, that's the unknown. So we now have an equation with only one unknown letter, x. So we're going to solve for the letter x. That stays the same. We distribute this, get a positive 15x. Negative times a negative gives me a positive. Now I have a negative 3 times a positive 4 gives me a negative 12. Now my next item in solving equations is to group like terms. I get 17x. I'm going to take this negative 12, transpose it to the other side. On this side it becomes a positive 12 opposite sign on the other side, or subtract 12, or add 12 to both sides here. This now becomes a 17. This is a 17. Divide both sides by 17. X equals 1. Wow. So now we have one of our ordered pair members. We have a 1. What we don't have is the x yet. So I'm going to take equation 1, rewrite it. I now know that my x value is 1. I put it there. 5 times 1 is 5. Y equals 4. Now I want to solve for y. So I transpose my 5. On this side it becomes a negative 5. 4 minus 5 is a negative 1. That's my other member. And if we were to graph it, we'd see that's where they would intersect. And if we now put that in each of these equations, we see that this ordered pair is a solution. And the method we used was substitution. That's what we're illustrating here. So in review, you have your two equations. You're looking to solve for one of the letters. It could be x or y. You then solve for it. Then in the other equation, you put the value for y where y is. That's the process of substitution. You multiply through, collect like terms, solve for the variable, then take that variable, put it in either of the equations, and solve for your other letter. And then you should check it too. Okay, the process of substitution. Now, in this next one, example 5 on page 175, they're asking us to solve it by yet another method. This method is called elimination. And here we're going to change the equations into something that will allow us to actually add them. And then in the process of adding these lines, one of the letters eliminate or cancels out. So we're looking for techniques here as well. So our basic technique is to write the equations. We'll keep the original ones right there. So this will be 3x minus 2y equals 8. And this is 2x plus 5y equals a negative 1. Now, we want to do as least as possible, but we want to be successful. So the first part of this involves a little bit of creative thought. And you might say, well, what can I do to, let's say, this equation and possibly this equation, so that when I add them together, something's going to cancel out? Well, I see here a negative and there a positive. If this number was a little larger, if this were, let's say, a 10, and this were a 10, a positive 10y and a negative 10y and a positive 10y, a negative 10 positive, that would cancel out. So this is what I'm going to work on. I'm going to show you the technique of how to do it. I like a little bracket around there. And in this case, I'm going to multiply this equation, every term, because I want to make this a 10, by a 5. Okay? And then this equation, I'm going to multiply every term by a 2. Now notice, they're going to be different equations, but they're still going to be equivalent. And I'll put them down here. So 5 times 3x is 15x. 5 times a negative 2y is a negative 10y. See, that's what I wanted to get. And then 5 times 8 is 40. Now, my next equation, I'm going to multiply it by a 2. This becomes a 4x. This becomes a plus 10y. And this becomes a negative 2. Now, what students often fail to do is to multiply every term by something. Once you don't do that, you no longer have an equation. See, this is an equation, and it's legal to multiply every term in an equation. That still keeps it an equation. It's not the same equation, but it's an equivalent equation. Now, when I put my line underneath it, I'm going to add them up. So this becomes 19x. Here, these cancel out now, and I get 38. Ooh. Now I'm going to divide both sides by 19, and I get x equals 2. Ah. One of the members of my ordered pair, similar to how we did substitution. Now we know that x is a 2. We can then use this equation. 3 times 2, that's my x value, minus 2y equals 8. So this is going to be a 6 minus 2y equals 8. I'm going to transpose that. This becomes a negative 6 over here. I now have negative 2y equals 2. Divide both sides by a negative 2. I get y equals negative 1. So that's our ordered pair, our unique ordered pair, where if we were to have graphed it, it's going to intersect there somewhere. Again, the graph is not accurate, just to show you the concept that we have here. Now, what method did we use? We used the method called elimination, where we had 2 equations in standard form that we lined up, and we modified each of these equations. Sometimes you may only have to modify one of them, or if you're real lucky, just it's already in a form that you could add something up and eliminate. But here, our first one, we had to modify both equations to make them into something that a term would actually cancel out. And this is what we get. Now, as we look at this next example, example 6, it starts on page 176, and it talks about Jasmine wants to use milk and orange juice to increase the amount of calcium and vitamin A in her daily diet. It says an ounce of milk contains 37 milligrams of calcium and 5 over here, 57 micrograms of vitamin A. And orange juice is this and this. And this is the amount that is suggested. I'm not going to read it all. It's in your book. So we've set up a little chart like this, and we're wondering what would be her ideal intake of these each day to meet these needs. How much milk, how much orange juice? Okay, so right from this little chart, we can set up our formula once we define milk as the X source, orange juice as the X source, Y source, excuse me. So here's our formula, 37x plus 5y equals 500. So there's our first equation in standard form. Then again, we're dealing with milk, x, 57x plus 65y equals 1200. There's our two equations in standard form, and we're going to use the elimination method that we just went over. Now as we, again, analyze these two equations, actually these numbers probably are the ones we want to eliminate. So here there's a positive 65. Here there's a positive 5. What do I have to multiply 5 by to make it a negative 65? And the answer is a negative 13. So as I multiply each of these items in my standard form by a negative 13, I get a new equation. Here's my negative 65y, and there's my negative 6500. But now, you notice when I rewrote equation 2 below it, I have one set of variables that will cancel out. That is, subtract out. And I only had to modify one equation. Again, throughout this, you need to be careful of your signs and double check your work. Now, when we did this subtraction, addition, depending how you look at it, we get this equals this. Then we divide both sides by a negative 424. And using our calculator, we get x equals 12.5. I then use the original first equation, put my 12.5 for x, got a value for x here, transpose this, subtracted that from both sides, get this, divide by 5, y is 7.5. So, this is my ordered pair, but what's my answer statement? Well, she would have to take 12.5 ounces of milk and 7.5 ounces of orange juice each day to meet these basic diet requirements. And that's what's going on. And again, you can look at it in the book. Also, by the way, if you have a graphing calculator, you can put this in there and see an answer. There's also something that we're going to look at in the next chapter that you can use your calculator to check. That's called matrix. And that's going to be lesson 4.2, where we take a look at the augmented matrix methods. All right, getting on to the last example, in section 1 of chapter 4, it deals with supply and demand. And it says the price supply and price demand equations for the sale of cherries in a large city are this. This is the price supply and this is the price demand. And again, this deals a little bit with economics that I think we covered it a little bit in chapter 2. So the first thing they're asking us to do is if we had $2.09, what would be our X value, that is the amount of cherries for the supply and the demand. And I've color-coded them in blue and red. So I put the for the price, 209 there, solved it for x, and I get 19. If I put the 209 in the demand equation, I get x is 9.55, just by substituting and then solving. And then they said, how about if the price was $1.32 per pound? Well, again, I put it there for the supply, and I put it there for the demand, and we get 8, and we get 13.4. Now, these are ordered pairs, and if I put those ordered pairs on a graph and were to graph them, I'd get a graph that looks like this, and this is done very well in your textbook right there, figure 4. And you see they do intersect at a point, and we call this point the equilibrium, which is to find the equilibrium of price. Now, I used a little different technique than the textbook. They suggested maybe you could use elimination. I used that if this P and this P were the same, I just equated this to this. That's what I've done here. So this equals that. This is P equals P. And then I solved it for x, and I got x equals 12. Then I took my 12, put it into one of the equations. I guess I did it, this equation here. By the way, there should be an x there. There's my 12, and I get P then is 1.6. Now remember, P is sort of like the y equals 1.6. So our point then of equilibrium are the coordinates 12 and 1.6. And if you look at our graph, that's what we got. So if we have at 12 pounds of cherries, our best sales will be at this particular amount. Good luck on your mastery for 4.1. We'll be going on to 4.2.